Dipole, dipole. And again, this is where NH3 comes into play. The concept here, so it has a name, called hydrogen bonding. And it's a little confusing because of the word bonding. Alright, so as I go over this, first period had a very tough time meeting the criteria for hydrogen bonding to take place. Okay, there are 2 items that are required. Alright, in order for hydrogen bonding to occur, both items have to be met. Alright, AP loves to trick students in this category where they offer just one of the 2. And if only one of the 2 is offered, then you cannot have this category. You need to have both of the criteria that need to be met. Alright, so I'll show you what to look for. Here are the 2 items. Item 1, look for a hydrogen, duh, bonded to N, O, or F. And the reason why this needs to be there, well, it has everything to do with electronegativity, so I'm going to explain that in a little bit. But anyway, that's the first requirement. And then we need an interaction, so I'm going to put interacting with. And here's criteria number 2, criterion number 2. Lone pair associated with N, O, or F. Okay, so again, the 2 items that need to be met are here and here. So one requires the actual H, the other requires a lone pair. Alright? Regardless though, you need to make sure that these elements, or one of these elements, has to be in play. Alright, so if you have a bromine, that's not going to work. Okay, now, the reasoning between, the reasoning with hydrogen needing to work with N, O, or F in both cases is a huge electronegativity difference. Because generally speaking, these 3 are probably some of the most electronegative elements on our periodic table. So this huge electronegativity difference creates a very strong dipole. Alright, so if we have a bond dipole to consider, if we have H with N, or H with O, or H with F, those are the strongest bond dipoles possible. Okay. Also, what ends up happening here, as to why I call it an exception, is that because of this situation, hydrogen bonds outrank standard dipole-dipole interactions. Okay, so the best way to show how this works is by using NH3, because that was the example we had yesterday. So I'm going to take a look at interacting to NH3 molecules. Okay, so I'm going to draw NH3 twice. Alright, now I got to draw at a weird angle. So, sorry in advance. So the first one, NH3, nothing fancy, lone pair on the end. Now, in order to show the interaction called the hydrogen bond, the second NH3 that I have to draw is going to have to go under the first one. Okay, so I'm going to draw the second one underneath. Okay, so let's take a look at both of the requirements. And I'm actually going to take a look at the second requirement before the first one. Second requirement, need a lone pair associated with N, O, or F. Is that shown in NH3?
Yes.
Okay, So we have the lone pair here that we're going to take a look at, especially because this one, there's no interaction with the second molecule, huh? Okay, so here, this lone pair, and then now it says I need to look for an H bonded to N, O, or F. Is this H bonded to N, O, or F?
Yes.
Okay, so the interaction is between these two items. And again, we usually draw a dotted line to indicate an intermolecular force. So this dotted line corresponds to a hydrogen bond. All right, so again, keep track of the lone pair, keep track of the hydrogen, make sure both criteria are met in order to show a hydrogen bond interaction. All right, so I mentioned that AP loves to trick students in this topic. Let me show you where they do this. Alright, so instead of NH3, we'll take a look at CH3F as to how we can set this up. Alright, I'm going to draw the fluorine to the right because I'm running out of room on this sheet of paper. Okay.
Should not be
Now, knowing that we need to interact a lone pair to a hydrogen, right? I'm going to draw the second CH3F molecule to the right, and I have the hydrogen here. Okay, so in other words, draw second one the same way. All right, again, we're looking at the two requirements. And it's easier in my perspective, though not necessarily for you guys, that I look at the second requirement to begin the problem. So I'm looking for a lone pair associated with N, O, or F. All right. So here, the only lone pairs to work with are on the fluorine. So is it eligible that way?
Yeah.
Okay. And then let's look at the first requirement. Is H bonded to N, O, or F? Is that true?
No.
No. Okay. So C to H is not eligible for hydrogen bonding. So in terms of the interaction here, there's no hydrogen bonding that exists between these two molecules because it only meets one of the requirements. It only met the lone pair requirement. All right, these hydrogens, they cannot hydrogen bond because they're not attached to N, O, or F. They're attached to a carbon. All right, so here, there's no hydrogen bonding. So in terms of the interaction between these two, since no hydrogen bonding occurs, well, what can it offer instead? Dipole-dipole instead. So here, this is dipole-dipole only in terms of hydrogen bonding. So dipole-dipole exists. So be careful with that. AP has tricked countless students by going, all right, what is the strongest interaction between two CH3F molecules? And they go multiple choice. A, dispersion. B, dipole-dipole interactions. C, hydrogen bonding. D, ionic. Don't pick ionic. Okay. So here, right, if you had those four as your options, the strongest interaction is dipole-dipole, right? All right, does dispersion exist though?
Yes.
Yes, okay, but that's not what we're considering here. We're looking at highest rank. Okay, so for hydrogen bonding, here's one thing to wrap it up. Okay. We saw that two CH3Fs, you cannot perform hydrogen bonding between them. We saw that with two NH3s, you could do hydrogen bonding between them. So to wrap this up, Here is a practice free response problem. What if you had one of each? All right, so again, it says we need to draw and label the strongest interaction between an NH3 molecule with a CH3F molecule. So, your choice how you want to draw it. But when we grade it, or when an AP grader looks at your response, okay, they're going to be looking for the interaction itself with the correct label. You can draw it in any direction you want. They're just looking for the interaction there. All right, so draw the two structures and show the interaction that takes place in terms of the strongest. I'll give you a couple minutes to work on it. Yes, it does ask you to draw things. Now you might be thinking, all right, what part of the interaction is needed here? Now remember, CH3F could offer the lone pair part of the requirements, right? Okay. So the missing requirement that this one does not have is the hydrogen itself, right? Here, NH3 can offer the hydrogen because the hydrogen is attached to a nitrogen. So I want this interaction to work. Okay, I don't need the lone pair. So in drawing CH3F, knowing that I'm going to use this hydrogen, I should put the fluorine on this side now because I need the lone pairs. Okay. So here, I recognize that the lone pair, which is on the fluorine, which is the second requirement, can interact with the hydrogen here because it's bonded to an N. Okay, so here, the interaction works. So, what's very confusing to most people is that CH3F cannot hydrogen bond with itself. But CH3F can hydrogen bond with something else if that something else can offer what it's missing. That's tough. Okay? So generally speaking, on an AP exam, if you're not told to work with one of each, you're just told CH3F, can it hydrogen bond by itself? No. Okay? But if I interact it with something that can offer what it's missing, then the answer is yes, it could. Alright, so be careful on the wording of the question. Alright? Feels like with AP Chem in this topic, they're really testing your English. They're not really testing your chemistry. Alright, so that's unfortunate for people here. Okay, so again, this is a hydrogen bond. So again, little dotted line to illustrate the interaction. Guys, okay, so to try to summarize what we have so far, okay, out of all of the categories we've discussed, the weakest one is dispersion only, okay, and then next in the ranking system is dipole-dipole, and then next is this hydrogen bond. So of the three, hydrogen bonding is the strongest intermolecular force. Okay, we know we have something that's even stronger, which is ionic, but you know we don't have to address that again. There's one last category. Ion dipole. Okay, as you would expect, if I want an ion dipole, can I have two of the same molecule? No.
No.
Okay. I cannot have two of the same molecule. Alright, because I cannot be an ion and have a delta plus delta minus at the same time. Alright, so we're not looking at that. So here, in order for this interaction to work, I need to work with two different molecules. Here's how it's designed. we need to have a full charge. That's an ion, right? And that full charge is going to be attracted to a quote-unquote partial charge. Partial charge means the delta plus, delta minus. And it's only one of the two, right? Not both. Of another molecule. Okay, so long story short, the first species has to be an ion. The second species has to be something that's polar. Okay, that's all we need. So I can just draw a quick one just so that you can see. So if I have Na plus, and let me just use CH3F again. Okay. Now here's the thing. If I have Na plus, in order for this interaction to work, do I need the delta plus or delta minus side?
Delta minus.
I need the delta minus side, right? So if I have CH3F, where's the delta minus side again?
F.
The fluorine. Okay. So here, you need to put the fluorine on the left to interact with the Na plus. Okay. The rest of the structure I can leave that alone with H's. So my delta minus is over here. Delta plus is away from the interaction. Okay. So this is an ion dipole. Alright? So in terms of the ranking system, would you consider ion dipole as stronger or weaker than hydrogen bonding?
Stronger.
Stronger, because we have ion, right? We know ionic is really strong. Alright, so if you're struggling with ranking everything now, I'm going to put it all together into some really ugly looking chart. Okay. So, intermolecular forces overall. Okay, and I'm going to list it from strongest to weakest. Okay, so I'm going to list all of them going downward to the weakest one. Okay, I'm going to have another column that deals with charge type. And then I'm going to have another column, for now, it's going to be just called duration. Alright, so the strongest intermolecular force that we would work with is actually ionic. We saw a little bit of that yesterday, where ionic can qualify for both inter and intra. Right? So in terms of charge type, with ions, we have full or partial charges?
Full.
Full charges. Okay, so I'm going to put full. And in the case, for example, of sodium ion, is sodium ion always a plus charge?
Yes.
Yes, right? Sodium, no other charge besides plus charge. So in terms of duration, you put down permanent. Okay. Now, after ionic, we have ion dipole. That's the next rank. Okay. So here, in terms of the charge type, rather than completely full, we have full with partial, right? Because we have full charge with the delta. However, can we still call both of these permanent?
No.
The answer is actually yes. Here's, go back to the structure, or back to the example we just did, okay? In terms of permanence, isn't the fluorine side always going to be delta minus?
Oh, yes.
Yeah, okay, permanent. Okay, so if you're wondering what's a different answer to this category, we're not there yet. After ion dipole, it's going to be hydrogen bonding. Alright. And then in terms of charge type,
No
do
partial
we have
charge.
full anymore?
No.
No. So we have partial with partial. Okay, and then I have to put a little note in parentheses, high electronegativity difference. Reminder about that. Alright, and then for hydrogen bonding, since we're still working with deltas, and we're kind of working with lone pairs here, the duration is still considered permanent. Okay, if not for hydrogen bonding, what would be next? Dipole, dipole. And this is standard, huh? So it's not anything extreme, but we're still working with partial and partial because it's still delta with delta. And then here I'm going to leave a note, standard. Okay, so we're not too concerned about high electronegativity differences. Again, with dipole, right, we're not allowed to change where our delta pluses or delta minuses are, because delta minus in this example is always going to be with fluorine, right? So it's still permanent. What's our weakest one?
Dispersion. Or yeah, covalent.
Okay, so dispersion is considered the weakest. Okay, now for the charge type. We still get delta pluses and delta minuses. We do. Okay, so we still get partial. And notice I'm only writing partial once. Okay, because it's possible they're only looking at one atom, huh? Okay, so here, in terms of partial, could be just one atom. And reminder, with dispersion, it's not permanent. What is it instead? Temporary. Okay, so hopefully you can see why the ranking system worked out this way. All right, now what was our one exception again? For dispersion, where we can outrank?
Polarability.
Okay, so again, there's a possibility with polarizability here. Polarize and outrank. Alright, so that's your list in terms of the ranking systems for intermolecular. There's a lot going on. I know it takes a while to let all this information somehow sink in. Alright, so I'm going to stop at this point. We're completing our responsibility. We have some time with the rest of the